In this video, we are going to take a closer look at electron configurations. So, as a reminder, an electron configuration is just a way for us to represent how the electrons are arranged in an atom within the orbitals. So if we look at an electron configuration, we can determine the energy levels that the electrons fill to, also the orbitals, and the number of electrons that are found within the orbitals. As a review, if I were to write the electron configuration for potassium, I would see that potassium has 19 electrons, and using my energy level diagram, I would come up with an electron configuration that looks like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. You may want to pause the video now and see if you can determine the electron configuration for silver. If you determined the electron configuration for silver, again you would have noticed that silver has 47 electrons in a neutral atom, and so my electron configuration is going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and 4d9. Okay? Each atom, as we know, has a unique electron configuration, and so we can go backwards and use an electron configuration to identify the following atoms. So if I were to take a look at the electron configuration here, 1s2, I can count the number of electrons and decide that 2 plus 2 plus 6 plus 2 plus 4 equals 16 electrons, and in a neutral atom, sulfur contains 16 electrons. Okay, the same holds true for nickel, or for my next example, if I add 2 plus 2 plus 6, that gives me 10 electrons, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 8, and I get a total of 28 electrons. Okay, and I can identify that as nickel. Okay, within an electron configuration then, an electron configuration can be broken down to show us the number of valence electrons and the number of core electrons within an atom. Okay, some important vocabulary then is a valence electron is referring to the outer energy level electrons. Okay, so these would be the electrons that are farthest from the nucleus. Okay, our core electrons then are going to be those inner energy level electrons. Okay, so these are the electrons then that are the closest to the nucleus. So if we look at our electron configurations listed here, in an electron configuration 1s2, 2s2, 2p6, 3s2, 3p4, we see that the highest energy level that we fill to is the third energy level. And within there, we have 2 and 4, so we get a total of 6 valence electrons. Okay, the remaining electrons that are closer to the nucleus in the first and the second energy level add up to 10 electrons, and so we end up with 10 core electrons. Okay, in my second example, again, I'm going to go to the highest energy level, and in this case, the highest energy level is the fourth energy level. And in that fourth energy level, there are 2 electrons, and so I would end up with 2 valence electrons, or 2 electrons that are farther from the nucleus, and the other ones add up to my core electrons. Now, if I wanted to identify the atom here, I would add up the 2 valence electrons plus the 26 core electrons, and I'm up with a total of 28 electrons. Okay, and if I wanted to determine the element that is, I could refer to my periodic table again and say, okay, nickel has 28 electrons. Now, if we look at letter A here, let's say we wanted to identify another atom that has the same number of valence electrons as letter A. So the first thing we would do is determine that in letter A we have a total of 16 electrons, and on my periodic table I can see that 16 electrons is the element sulfur. Okay, if I were to write the electron configuration for any of the other elements in the same column, and picture columns going up and down, as sulfur, I would see that all of those electrons would have, all of those atoms would have 6 valence electrons. So the elements O, Se, Te, and Po are all going to also have 6 valence electrons. Okay, and if we notice, or what we will find, is that elements that are in the same column are going to have the same number of valence electrons. Writing an electron configuration can get long and kind of time consuming, and so there is a shortened version of an electron configuration that we can use, and this is known as the noble gas notation. So electrons can be shortened using what is known as noble gas notation. So the first thing we should recognize is that the noble gases are a group of elements that are found on the periodic table. So if you take out your periodic table and you look, you will see that on the far right-hand column, okay, on the far right-hand side of your element, or of your periodic table, you have the noble gases. Within this family of elements, it starts with helium, okay, and moves on to neon, all the way down that group. Okay, so those right there are known as the noble gases. Again, we can shorten electron configurations using the noble gas configuration. So if I looked at an example like this, I have an atom that has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p4. This electron configuration can be shortened using this noble gas notation. Where this comes from is if I were to write the electron configuration for neon, which has 10 electrons, I would end up with this: 1s2, 2s2, 2p6. And so instead of writing that, I can put the element symbol neon in brackets and know that that is representing this beginning part of my electron configuration. And then after it, I add the additional part, the 3s2, the 3p4. Okay, the same holds true for my next example. In this example, you can see I have quite an extensive electron configuration, but if I look, I have shortened it by writing Ar, argon, which is one of our noble gases, and the electron configuration for argon ends at 3p6. So I can shorthand that by taking that part of my electron configuration, bracketing it, put the element symbol, and then adding the additional part. So again, noble gas notation is used to shorten an electron configuration because the noble gases represent full energy levels. So instead of writing out the entire full energy level, we can shorthand it with the noble gas notation. Okay, so let's look at a couple more examples. Let's say we want to write the electron configuration using the noble gas notation for chlorine. Okay, the first thing I'm going to do is I'm going to find chlorine on the periodic table, and I'm going to look backwards and find the noble gas that comes before chlorine. So if I locate chlorine on the periodic table, the noble gas that comes before it is neon. Okay, so directly after chlorine there's argon, but the noble gas that comes before it is neon. Okay, so the neon part of my noble gas, or of my electron configuration, is going to go in brackets. And again, if I need to, I could write this out and recognize neon is 1s2, 2s2, 2p6. And so now I'm just going to add the after part of it. And the after part of neon is going to be 3s2, 3p5. Okay? Again, neon has a total of 10 electrons. So when I add these extra electrons in, 2 and 5, that's going to give me my total of 17 electrons, which is what chlorine is. In the next example, I'm going to take a look at germanium. Okay, again, I'm going to find it on the periodic table. It has an atomic number of 32. So I locate it on the periodic table. The atomic number is 32. Directly behind it is argon. And so my noble gas configuration is going to start with argon. Okay, after argon then, the additional electrons go to the 4s2, the 3d10, and then the 4p2. Okay, if I were to add up, argon has 18 electrons. If I add it to the 2, that gives me 20, plus 10 gives me 30, plus 2 more, that's where I get my 32 electrons. Okay, so using the noble gas configuration is just a shorthand way of writing out really long electron configurations. And it's based off the idea that noble gases always have full energy levels, and so we can sub those in for all of the completed or the full energy levels.